Hello everyone, I'm Yinjun Wu, the CEO of RisingWave Labs. Today I'll be talking about cost-efficient stream processing with RisingWave and ScyllaDB. RisingWave is a streaming database, while the ScyllaDB is one of the best NoSQL database systems in the world. And I'll show you how you can use these two different systems together and to power your real-time application. I'm the CEO of RisingWave Labs, and people call me the Chief Everything Officer. Before running this company, I was at AWS Redshift, the data warehouse team at AWS. And prior to that, I was doing research about database systems and stream processing at IBM Research Armadan. I earned my PhD in databases and stream processing systems. So essentially, I have been in the database and stream processing domain for probably over a little bit more than 10 years. Actually, a lot of things happened over the last 10 years in the stream processing domain. And today I will show you about what is RisingWave and the use cases of stream processing and the challenges and solutions. I will definitely show you a demo to demonstrate how you can use the modern advanced technology to simplify the development of stream processing applications. So first of all, what is RisingWave? RisingWave is a distributed SQL streaming database, which is purposely built for processing your streaming data. And we open sourced the database in April 2022 under Apache 2.0 license. And we have already, over the last 2 years, we have already gathered 6,000 GitHub stars and 150 GitHub contributors. We have definitely a lot of Slack community members, and the system has already been deployed over 150K times using Kubernetes deployment. So let's talk about a little about what is stream processing. Why we need stream processing? Essentially, every time if you want to build applications like ad recommendation, stock dashboarding, travel booking, something like that, you definitely want to provide your audience or your customers a real-time experience, right? And if you want to build such kind of real-time applications, then you will definitely think about, how I can process my streaming data from my, let's say, database systems or messaging queues, right? So how do we build such kind of streaming application or real-time application? Typically, what we do is that people will definitely have an operational database like MySQL, Postgres, right, or CockerDB and some others. Or probably they can have data coming from the messaging queues like AWS Kinesis, Repanda, Kafka, Pulsar, and many others. And once we get the streaming data, we need to do some processing, right? We do some processing, extract the knowledge, gain real-time insights, and then send our data send the results, send the real-time insights into ScyllaDB, so that ScyllaDB can power your real-time apps, right? Or probably a web page, or probably a dashboard, or something like that, right? Definitely, that's how we build a stream processing app or the real-time app. So the question here is that how we can extract real-time insights. Here we definitely want to have, let's say, a stream processing system. People typically use KSQLDB, Samza, Flink, Spark Streaming, and many others. Well, these systems can definitely work, and it works perfectly if your application is not complex enough. For example, if you just want to do some filtering, projection, you can definitely use any of these systems, right? But the problem here is that these kind of systems are kind of expensive, especially your application is complicated or you need to handle a large amount of streaming data. Then why stream processing is so difficult? Well, the key challenge here is that stream processing is all about continuous processing of your streaming data, and you actually need to think about how we can manage the internal states for the stateful operators such as joins, aggregations, and time windows, and many others. So let's just think about we just want to build a monetization application. Let's think about we want to join two different streams. One is the impression stream, and the other one is a click stream. In this example, we actually need to maintain two different states. One is the hash table for the impression stream, and the other one is the hash table for the click stream. So every time a new event comes into the impression stream, we actually need to check, okay, whether there's a match in the hash table for the click stream. If there's a match, we send the output, right? We generate output and send to ScyllaDB so that ScyllaDB can power your application, can show you your web or probably your dashboard, the results, right? That's how it works. So we need to think about, well, I mean, if the scenario or the streaming workload is not big enough, definitely, I mean, it's easy. But the problem here in stream processing is that you definitely may have the burst. You definitely probably will come from the burst streaming workload, right? What we can do here? I mean, here the key thing here that we need to think about, like, how we can measure internal states, because where the states can grow as the workload fluctuates, right? Or probably it can shrink. If it shrinks, then we need to think about, like, how we can reduce the number of machines, right? So basically the question becomes that how we want to measure internal states. Well, how do we do that? The traditional solution, I mean, inspired by the MapReduce, was to couple the compute and storage, and we can probably partition the states and send the states into different machines. And that's how all these existing systems work. Think about, okay, let's say that we need to measure a state, and we have 3 machines. What the people will do is that they will partition the states into 3 different machines, and so that every single machine only need to focus on computation, doing computation on its own state. Well, things can work great, but again, I mean, if the workload fluctuates, your state will definitely grow. And for every single machine, as we all know, the memory and the disk is limited. If the states grew too big, then what will happen? I mean, system crash, right? And probably you will no longer be able to power your ScyllaDB and to power your real-time application. Right? That's a key issue here. So what we can do to solve this problem? Well, we all know that nowadays we are living in the cloud era, right? Everyone is using AWS, GCP, Azure, or some of the cloud, right? So we can essentially reimagine how we do stream processing by leveraging the modern so-called decoupled compute and storage architecture. And that's how RisingWave does. So let's reimagine, okay, how we can do join 2 different streams using RisingWave. As I just mentioned, I mean, in RisingWave, it actually uses decoupled compute and storage architecture. So where the internal state is managed in RisingWave, well, it actually manages the state in S3 or in some other object stores, right? In GCP, GCP has its own object store. We manage the state there. So if we confront the workload burst, then we do not need to worry too much about, okay, whether we need to deal with the scale in or scale out, something like that. The only thing we need to think about is that basically we actually don't need to worry too much about that, because S3 can manage the state automatically, because we can assume that S3's volume is unlimited. Well, definitely things look great, but there's a huge problem, which is S3's latency is kind of high, can be as high as 100 milliseconds, right? So so how do we address that problem? So in RisingWave, we introduced the so-called tier storage. So the basic idea is that we can leverage structure called log structure merge tree, and which stores the recent data in local machine, while the older data is periodically compacted into lower levels, which is stored in S3, so that you do not need to worry too much about the S3 latency, because most of the time you only hit the cache in the local machine. That's how it works. So with this architecture, I mean, we actually have a better user experience. Why? Well, think about that. Okay, for the conventional stream processing system, they actually manage the states in local machine, while RisingWave manage the internal states in the remote machine. So that okay, when we deal with the failure recovery or elastic scaling or so-called dynamic scaling, things can be much easier. Why? Think about, okay, what if a node failed? If a node failed, the only thing, if you use conventional stream processing systems, then actually you have to boot another machine and actually reload the state from your checkpoint into that machine, right? And it can probably take probably an hour, half an hour, I don't know, it totally depends on your state size, and before recovering, right? But for RisingWave, the things can be totally different. If the machine failed, then it failed, because we can always just boot another machine and ask that machine to reload the state, actually directly without loading, directly read the states from the remote object store. That's how it works for failure recovery. And then let's think about the elastic scaling. Well, similarly, if we similar to the failure recovery, let's think about, okay, how we can do in the traditional stream processing system. Well, traditional conventional stream processing systems could have a hard time to deal with the dynamic scaling, because if we want to scale out, we actually need to parse the entire cluster and reload the states into a new machines, and then it can take probably a few hours, probably or 30 minutes, right? Totally depends on state size. But in RisingWave, again, the experiment is totally different, because the new machines can be just created. The new machines can directly reload the states from the S3 without thinking about, okay, how I can manage the states. Right? Okay, now it's the demo time. So I will show you two demos. Let's assume that, okay, you now have the first one is the real-time ETL. So basically, you do extract, transform, and load data from Postgres, one of the favorites or one of the most popular database systems. Do some transformations and send data into ScyllaDB. How can we do that? I don't know how many lines of code you have to write using some other stream processing systems, but in RisingWave, you only need to write 2 lines of code. The first line is that you can just create a source called, let's say, call it mypg, right? And you set a connector's name to, let's say, Postgres CDC. With this line, RisingWave will directly connect to Postgres, and it will continuously pull data from the Postgres. And the second line you need to do is that you just need to create a sink called, here I call it myScylla, right? S and followed by a select statement, S select column 1 from mypg, and then don't forget to write a line called with connector equal to Cassandra, because for ScyllaDB speaks Cassandra protocol, right? With these 2 lines, you will be able to create a streaming pipeline that continuously ingests the data from Postgres, do transformations, and then send data into ScyllaDB. Well, definitely, I believe that was definitely a pretty simple use case, right? But some people sometimes will say, okay, look, my use case is more complicated. I probably really want to consume data from multiple data sources, do joins, and do all kinds of magics, and then send it into ScyllaDB, right, to power my real-time application, right? Sure, we can do that. Let's assume that, okay, we have Postgres as Kafka, right? And you want to have very complicated the computation logic, right? Conventionally, if you want to use conventional system to do this, you probably really want to have, let's say, a stream processing system plus Kafka, and then plus stream processing system plus Kafka, something like that, right? It's so complicated. What a mess, right? But in RisingWave, the thing will be different. The only thing you need to think about is that, okay, I can create materialized views, and I actually can create materialized views on top of materialized view, so that the logic can be actually chopped into smaller pieces, and every piece is wrapped into a materialized view. So let me show you the code. So in the computation here I ignore consuming data from Postgres and Kafka. So let's say that we have already connected to Postgres and Kafka. The next thing we will do is that we can just create materialized views, right? Here I use example like create materialized view MV1 as followed by a select statement, and similarly we create a materialized view 2, right? And if we want to do computation using the material results maintained by MV1 and MV2, then the only thing you need to do is that you can create a materialized view called MV3 as select something from MV1 and MV2, right? That's basically a join. And once you get an MV3, essentially it's the real-time results, right? You can just create a sync called create sync my Scylla as select something from my MV3 with the connector equal to Cassandra, and that's how it works. So again, well, that's how simple it is to use RisingWave and ScyllaDB to power your real-time application. So to conclude, modern companies definitely want to gain insights from their real-time data, right? Because more and more data are generated in real time, and we really care about the real-time results. Nobody wants to see the stale results, right? And RisingWave plus ScyllaDB can work collaboratively to reduce the stream processing cost while attaining top performance. Yeah, that's all my talk. I'm Yinjun Wu. If you're interested in how to build stream processing systems with RisingWave and ScyllaDB, don't forget to reach out to me, and you can follow me on LinkedIn, Twitter, or some other places, or probably you can join our Slack community channel. Thanks.